Hi everyone, and welcome to the LedaFlow 2.8 release webinar. My name is Camila, and I'll be moderating our session today. Today, you'll hear from my colleague Wouter, product champion for LedaFlow, about the new release, the new features and benefits offered to the users. Before I pass the word on to our presenter, please note that you all are muted during the session. So if in case you have any questions during our presentation, please type your message on the question panel that is on the right panel. After the presentation, we'll answer as many questions as possible. Now I would like to invite Wouter to present the new release and take it from here. Enjoy the session.
Thank you, Camilla, for the introduction. So hi everyone, I'm Wouter Dijkhuizen. I'm the product champion for LedaFlow, and I will take you to some of the features of LedaFlow 2.8 today. So the contents are as follows. So first of all, I will go over some of the improvements that we've made in the simulators. So an overview of the CO2 capabilities in LedaFlow, some improvements to slug capturing, and some diverse other improvements. And then finally, the GUI improvements that are in LedaFlow 2.8. Okay, the reason that I'm talking about CO2 here is that recently we've decided to commercialize all of the work done on pure CO2 simulation, which is coming from a research project called CO2 Fact. So the objectives of this JRP were to qualify multi-phase flow software for CO2 transport and injection. And also, as part of this, we have begun to extend LedaFlow to CO2 with impurities, but that is not commercialized yet. So maybe next time you can hear from that. So this project, it revolves around a series of very interesting experimental campaigns for both pure CO2 as well as CO2 with impurities. So these experiments, they consist of a lot of multi-phase flow experiments that are at steady state with many different inclinations, both uphill and downhill, which is quite interesting. There's some experiments about phase change by different means. So the facility that was used for these experiments can be used it can be heated up and cooled down by different means. And also some experiments were done by using a choke valve that also resulted in phase change. So there's a lot of focus on the mass transfer there. Some experiments around shut-in and restart were done. There's some experiments around depressurization to the atmosphere, and fluid hammer experiments, and finally some displacement experiments. So these experiments, they are proprietary, so I can't show you too many of the results here, but one of them I've shown on the right here. That is a fluid hammer experiment. That one was published. You can see the reference at the right bottom of the screen. So this experiment, the flow loop was closed in with two fast closing valves. And then it's all about trying to match the pressure amplitude and period of the oscillation. So you can see the pressure wave is bouncing back and forth between the closed valves. You can see that we have quite a good match between LedaFlow and the experiment. So this shows just one of the experiments. It shows that LedaFlow does a good job for CO2. Okay, so let's get back to okay, why are we doing CO2 simulations with LedaFlow? What makes LedaFlow suitable for this? Well, first of all, the thermal equations in LedaFlow have always been formulated in terms of enthalpy. So we conserve enthalpy. We don't have equations that are based on temperature, which is good because this is the only universal way of solving this that works for any kind of composition, whether it's an oil composition or natural gas composition, it doesn't matter. Pure CO2 also fine. So this is fortunate for us. Then LedaFlow has a volume conservation equation. So that means that both the volume and mass are always converged at the same time, fully implicitly, which is important for fast transients, like for example this fluid hammer case that I showed earlier. We are using multi-flash in LedaFlow, which means that through multi-flash we can support many different equations of state, like Span and Wagner for pure CO2 or GERC for CO2 with impurities. And finally, LedaFlow, it contains a what we call the non-equilibrium mass transfer model. So that means that only the flow into the pipe network, so that's the boundary conditions, they are flashed in the dynamic model. But basically what that means is that we don't do any flash calculations inside the pipe. And that also means that any discussion on whether to use PT or pH flash calculations, it's irrelevant for the dynamic model. This non-equilibrium mass transfer, it supports subcooling and superheating, which is physically correct. And we have full control over the rate of phase change. So this is a kinetic expression, and it's easy to adjust this as we learn more about how the system behaves. Then a little bit about the single component module. So this is not only used in LedaFlow for CO2, but it's also in use for steam water systems. As a matter of fact, that is what it was developed for originally. So originally this was implemented for SAG-D applications, which means steam injection into the ground. Then later it was used for steam transport pipelines, for instance, the steam network underneath the streets of Manhattan in New York. And then now we're using this for pure CO2 pipelines and injection wells. So all of this technology is shared. So the special feature of this single component module is the mass transfer term, which is different from what we use for PVD tables and other composition tracking applications. So the mass transfer, it's a true phase change, of course, for a single component system. It will be limited by heat transfer rather than diffusion, which is logical because if you have 100% CO2, diffusion does not play a role anymore. So then heat transfer takes over as the limitation. So this heat transfer rate is hard-coded in order to improve conversions because we don't really have a good model that does a better job. We have independent mass transfer terms for the dispersed phases and across the large-scale interface. So large-scale interface here means between the continuous gas and the continuous liquid phases. And the user has the option of tuning the rate of phase change to match experimental data, which was used during the CO2 project. And just as an example, what this expression looks like, this is just one of the mass transfer terms, which is for condensation of gas into the liquid phase. What we end up with is the rate of phase change is equal to the heat transfer coefficient H multiplied by a specific surface area A and multiplied by the subcooling, which means the saturation temperature minus the gas temperature, divided by the latent heat. So in the end, what we come up with is a rate of phase change, which is in units kilos per cubic meter per second. And then this will have the same effect roughly as if you were doing a flash calculation, except that the flash calculation will give you the steady state. And this is a kinetic expression, but the effect will be the same in a dynamic simulation. So in the terms of solver strategy, we ran into some issues when we tried to simulate some of these experiments in the project. So CO2 cases, they can be very difficult to converge, which is of course not really a surprise, but we found out exactly the reason why, which was quite interesting. So one of the reasons why we had to work a little bit on numerics was that pressure and temperature were tightly coupled. So this holds especially true around the rhythm line in supercritical conditions. So that means even in single phase supercritical conditions, it can be very difficult to solve this, even if there's no phase transition. The reason for that is that, for instance, the density, it can change over the course of a few degrees Celsius. It can change around, let's say, 50%. If you go from liquid-like to gas-like supercritical fluid. So that is one thing that we have taken into consideration. And the second one is, of course, that this mass transfer term that I just showed you, it depends strongly on temperature. So for both of these very different reasons, we had to do something to have a stronger coupling between the mass and energy equations. In order to do that, let's first go through the standard solution included in LedaFlow, which works very well for oil and gas applications. So there's really no issue to use anything else there. So that is the standard scheme that is shown in the left figure. So what we do there is during every time step we update the PVT properties first. Then we solve the momentum equation, then we solve the mass equation, and then there's an iteration loop around these two. That means that we iterate until both mass and momentum equations are converged, and only then do we solve the energy equation sequentially afterwards. That is not a problem. It's actually very efficient to do it this way, or as long as the PVT properties are not very sensitive to the temperature compared to the pressure. So this works really well for standard applications. But here we have to do something else, which is what we call the energy inside loop option, which is what we recommend for CO2 cases. So here we just put the energy equation inside this iteration loop that is around the momentum and mass equation. And the effect of that is that the energy, momentum, and mass equation will now all be converged at the same time. And then that makes it possible to handle these difficult CO2 cases, basically. And also, as part of this, we actually update the PVT properties during this iteration loop. So that means that we have a fully implicit solution in terms of density and enthalpy. Okay, enough about CO2. There's also some very nice other improvements in 2.8. So, for instance, on slug capturing, a lot of work was done on the slug bubble velocity in risers. So, as it turns out, the slug bubble velocity that was predicted by slug capturing in LedaFlow 2.7, it matched really well for short risers. For instance, the experiments that we have from the Tiller laboratory, the large-scale loop there, which is about 50 meters tall. So there we had a really good match using slug capturing, but it proved that the slug bubble velocity was too low for longer risers, which is exemplified by the unit cell model, which we know gives good results for long risers. So basically, we have a deviation for longer risers. So this has been improved in LedaFlow 2.8 by doing two things. So first of all, we've corrected the slug bubble velocity to better match the unit cell model, which improves things for long risers. And then secondly, what we've done is implement a transport equation for the slug bubble shape, which accounts for the time it takes for the bubbles to reach their final shape. So using this transport equation and the correction to the slug bubble velocity in general, it's possible to have a good match both for short as well as long risers. Just very briefly, some other simulator improvements. So we've also changed the steady state preprocessor. It now uses a pH flash instead of a PT flash. This is in order to enable phase change in steady state for single component systems, for example, CO2. And just as a remark, I need to point out that this is only available if you use multi-flash PVT, so not if you're using GUTS for PVT, which is almost not used by anyone. We've corrected something for the non-Newtonian fluids. It proved that in the turbulent regime, the pressure drop was not correct. So this has been reworked, and we now have a slightly lower pressure drop only in the turbulent regime for non-Newtonian fluids. We have added a new option for the leak device to model autonomous inflow control devices. And that basically means that we have a leak device where the pressure drop depends on the density and viscosity of the different phases. There's a whole lot of different tuning coefficients, so you can model the exact configuration of the inflow control device. Multi-flash PVT has some more options. So now we have a fallback option in case LedaFlow doesn't support a certain equation of state or any other option in multi-flash. It's possible to let multi-flash read the multi-flash file that contains the fluid configuration. It can be read directly by multi-flash, so that is quite useful as a fallback. And also we're supporting some more equations of state now, like GERC 2008, which can be nice for CO2 with impurities, and some old legacy Payne-Robinson and SRK equations of state. And also helium has been added as a component because that was a request by one of our customers. And then finally, in terms of simulator improvements, we have the option now for the PID controller to dynamically switch between automatic, manual, and freeze mode. So previously it was only possible to set this as a general setting, but now it's possible to do this as a time series, which enables to put the PID controller kind of on hold during a simulation, which can be quite useful. Okay, I would like to finish this presentation by showing some of the improvements that we've made to the user interface and the workflow in general. So first of all, we've added the option of defining what we call ambient properties, which are just tables containing the ambient temperature and air-water velocity around the pipe as a function of elevation. So previously it was necessary to define these variables along the pipe as a function of the pipe length, which is kind of convoluted in order to do that. So this is a more logical and direct way of doing this. But the main benefit of this is that you can use one table for all the pipes in a network. So if you have a large pipe network, you can make a single ambient properties table and use it for all the pipes, which makes it much easier to set up, and also it guarantees consistency between the different pipes in a pipe network. And secondly, we now have the option of reading restart files with a different mesh. So if you have, for example, if you're using slug capturing and you remesh your case using a primary mesh, it's possible to use a restart file from a different simulation using a coarser mesh as a starting point, which can lead to quite significant time savings. Then it's possible to position devices now using true vertical depth, which is mainly useful for wells that are defined in TVD MD coordinates. So this comes in addition to MD as well as length coordinates. The flow regime plots, they now show text instead of just an index for the flow regimes. This is personally one of my favorite improvements because I was always looking at the user manual in order to figure out what exactly flow regime 4 was and other things like that. But now the plots, they actually show in text the flow regime. You can see that on the right bottom of the slide. So this is quite a lot more user-friendly, basically. And then finally, we've made some improvements to the Excel add-in. So we now have customizable units, just like what we have in the GUI. And also it's possible to extract the same variable for a different case or at a different time point. So that makes it much easier to compare different time points for a single case, or to compare different cases in order to have different profiles in the same plot. In case you rerun a simulation, the sample times that contain the data may have shifted a little bit because LedaFlow doesn't automatically, it doesn't exactly save at the same time for different simulations. So we've fixed that by automatically finding the closest sample if it has shifted. And then finally, we support pipe routes just like what we have for the plotting in the LedaFlow GUI. Okay, thank you.
Hello, thank you for your presentation. Can you hear me well? Yeah, can you hear me okay? Yeah. So let's go through the questions. So we still have some time, some minutes left. So in case you have any questions, please feel free to type them on the question panel to the right. First question we got is, how are phase change kinetics, such as boiling of CO2, handled in LedaFlow?
Yeah, so that ties back to my slide about how the phase change was defined for the single component model. So basically, the kinetics are based on on the multiple of the heat transfer coefficient and the specific surface area multiplied by the temperature difference with the saturation curve. So essentially, what that means is that the higher the subcooling, the faster the rate of phase change will be, which makes sense.
Great.
I can also mention that if you want to know more about this, there are some more details in the user manual, which could be interesting.
Great. Thank you for that. Let me see. I see we also got some more questions about practicalities regarding the webinars. Some colleagues that would like to have access to the recording so that I can maybe help to answer. So yes, the recording will be available to all the attendees and to everybody who registered. So in case you have other colleagues who registered to join but had any issues, couldn't be live watching us, so they will get access to the recording into maximum 2 days approximately after the session. I think that's the main questions we got up to now. So in case there were no more questions, I understand it was pretty clear. And in case there is further topics you would like to discuss or would like to know more, feel free to contact us and reach out through either by email to Wouter or through the LedaFlow website. I got one more question. When is it available for download?
Yeah, so LedaFlow 2.8 was released a few weeks ago, so it is available for download. And then if you're having issues with that, you can contact LedaFlow support and they can help you with the link. But I suspect if you're an existing LedaFlow customer, you should have gotten an email notification about this already.
Great. I think that's a very relevant question. With that, I would like to close the webinar for today and would like to thank Wouter for presenting the new features and the latest release, and would like to thank everybody who joined us today for the session. You'll get the recording, and in case you have further questions, feel free to reach out. Thank you.